However, we see in the results here in this simple OD example, the error is also small. So which means the neural networks can generalize to simple cases by training on complex cases. But what if the opposite way? We train the function using large quotient lengths. So we train on simple functions, but we try to test on complex functions. This would not work. You can see the error becomes large. So the same phenomena can be observed in many other systems and many different networks. Okay, this is sort of intuitive. But how can we understand this? As the first step, we try to quantify the level of extrapolation. So we have two spaces, one Gaussian process for training, another one for testing. Then how can we quantify the distance or the similarity between these two spaces quantitatively? This is a metric called W2 metric, as shown by the equation here. This is not a new metric. This is a metric exists for a long time. But this metric can be applied to measure the distance between two function spaces. Then for the example I showed before, we compute metric between all the spaces of training and testing in the two plots. Then let's look at what's correlation between my error and my distance between these two spaces. And surprisingly, they have a really good linear correlation in the low scale. So which means we can quantify the level of extrapolation by looking at the distance of these two spaces using the W2 metric. Okay, based on this, we developed a framework for reliable extrapolation. Let's assume in the first step, we have a pre-trained model, could be a foundation model, pre-trained on some data set. Now we have a new input V. Then we apply my pre-trained network on this input. We have prediction of U tilde. So we can compare the smoothness of my function for training and the new input, and also compute the W2 distance. If it's interpolation or my extrapolation smoothness, my W distance is smaller than some threshold epsilon, then I'm roughly confident, okay, my prediction U tilde should be correct or have small error. But if the distance between these two is too large, then my prediction would have a large error. Then we go to this domain. So we try to have another way or some extra step to improve my prediction accuracy. But this cannot be done by no information. But we need some extra information to correct my prediction U tilde. For example, we may have some new data set, but data set definitely is small. We assume we have like a small data set. Then we can do fine tuning or transfer learning. What is people currently frequently doing for foundation model? We have pre-trained foundation model. We do fine tuning on a new case. Then we hope the fine tuned network would work well for a new problems. But we did this before, much earlier, actually, even before the ChatGPT. Our first version of this work is in 2021. Or there's another paradigm called multifidelity learning. So this method has been well studied. I was not really saying well studied, but has been studied a lot in scientific computing. We can see my prediction of U tilde from my foundation model is low accuracy. But I have some sparse new data set. Then how can I integrate the information of two levels together to construct a high fidelity prediction? So it's called multifidelity learning. So in paper we have a lot of details of the method, how to apply this, and how can we do this efficiently. But I will not discuss today. But based on this new information, we can improve the prediction of U tilde. All the information could also some extra physics. You can fine-tune your network instead of using data. You can fine-tune network using the physics, using the governing equations, conservation laws. So this is a simple demonstration of the method. So this is a data set of the temperature and also the pressure of the Earth's surface from the years 1950 to 2021. For example, this is the data on the date January 1st, 2021. On the left, we have the temperature. On the right, we have pressure. Now we try to train a network, predict the pressure from the temperature, basically learn the correlations between the two. Let's assume we only train our network using the data set in the first 5 years. Then we try to predict for the later years. And you can see we have a larger error for later years. But the reason is this correlation between the two are evolving during time as we have global climate change. Which means for later years, actually it becomes more and more extrapolation. So that's why we have larger errors for later years. Then to improve this, we can do fine-tuning or transfer learning, multifidelity learning, assuming we have some extra data set but sparse on these 100 weather stations. Then for the same date, we apply this data set of this at these 100 dots to fine-tune our model. Then we can improve the accuracy and have a small error. So this is the extrapolation from a training data set, but we go to beyond. We try to go to a different setting in the testing data set. So this is a harder problem than interpolation, but let's consider an even harder problem. I call this as mission impossible. So let me first try to convince you this is indeed a hard problem and almost impossible mission. So this is a one-shot learning. So when we train our networks, we always have many pairs between my inputs and outputs. So then we do the prediction. But now let's consider we only have a single data point for training. So in my training set, I have a single image for input, a single image as output. But now I try to train network for the prediction of new case. Still, when we consider this setting in the PD scenario, right? If you have PD, but PD has some force inter or sorter. We try to predict the PD solution yield from the force inter of this input, and I have single pair of my input and output. But this is impossible even if we consider linear model. But even linear model requires 2 points. But here I don't have a single data point. I cannot even apply a linear model. Also, I consider this PDE is unknown. But I have no idea what's the equation for the PDE. I know there's some PDE, but no information about PDE is given. So I cannot do physics-informed training. Right? I cannot do what I did in the very beginning of pigs. This is not possible. I consider also there's no other information, for example, random tasks, which means I cannot do transfer learning. I cannot do meta learning. All these are impossible. But how can we solve this problem? Okay, so the only information I know is my system is not a random system. It's a system governed by some PDE. And for the PDEs, we know something about the PDE. We know there's a principle called locality. So which means, let's say in this square domain, I have a PDE, heat equation, diffusion equation, Schrödinger equation. So there's some equation imposed in this domain. Then if I cut a arbitrary small domain, a square here, a polygon here. So inside this square, inside this polygon, my equation, my PDE is still true. Right? This is still valid. So this is knowledge I try to leverage to develop a framework. So based on this idea, I will first propose a concept called the local solution operator. So it's a solution operator of the PDE, but defined locally in a small domain. So let me use the example of this small square to explain this idea. Okay, let's say we have a small square here. Because it's small, then we define, or to make this explanation easier, let's draw a local mesh. So we have some dots on the boundary of a small domain and some dots inside. but the small local mesh of local domain could be arbitrary. A polygon, we have some boundary points, some inside points. Let's say I pick a specific point inside the domain, denoted X star, the red point. I call this my target point. And all the boundary points, the blue points, I call this as auxiliary points. So omega auxiliary. Because we have the PDE imposed in this domain, then if you assume all the boundary values are unknown, are given, so by giving the boundary points and also the force, right, the forcing term in the PDE, also in this domain, then theoretically, my PDE solution on this domain is uniquely determined, which means I can have a mapping called G tilde with the input of all the boundary information and all the information of the X, of the forcing term. Then I can predict the PDE solution for any location of X star inside the domain. Okay, this is I call this G tilde as local solution operator. Now I try to have a machine learning model to train or to learn this G tilde. But as remember, so we only have a single data point, a single solution pair of U and F. So the way we generate a data set for training this neural network. So this neural network with input of all the boundary U, the solution and the forcing term, the output in the solution X star. So if I place my small domain, let's say in the left top corner, okay, then in this corner, in this location, I have the F value and the U value for this small domain, right? From in this data set, basically a small piece of my data set. I also have the X star, the U X star, and this red dot. Okay, this is my first data point. Then if I move this my so-called template. If I move a template in another location, then I can generate another pair of inputs and outputs. I put this another location, another data point, another location. Okay, a new data point. So this could be, you can do this in a grid, or you can do this randomly. Right? You put your template at random locations. You can generate many different data pairs for training your G tilde. Okay, now we can have a data set, and this G tilde can be trained. Then given this trained G tilde, we try to predict. So remember, eventually we try to predict the PDE solution for new input, for new F. So we cannot do this in, let's say, in one fold pass, as what we do usually in machine learning, because this is a special setting. It's a different setting. So what we do as follows. Let's say for a new F, let's assume my network, my PDE solution U is represented by a neural network, but it cannot be neural network. It can be other machine learning method you like. But here is a neural network as an explanation. Okay, my network solution, my PDE solution is represented by the neural network. Input is X, output is solution. I can apply my G tilde to as a constraint for this neural network. So what we do is, still we put the G tilde template at different locations of this solution. And we try to compute, okay, if my network prediction is U hat, what's the error between the current U hat and, sorry, the current U hat as some target location X or X star with compared to my prediction for my G tilde. Basically, I apply the G tilde into arbitrary small location, and I check, okay, at this small location, whether my network current prediction of the U is consistent with my G tilde, or essentially my G tilde represents some physics for this small location. So this is my loss function as a constraint of the physics. Of course, we also need a boundary condition or initial condition for new case. to determine uniquely the PD solution. But here I only show the loss function for the G tilde. Then together we can train this network for U hat for new F. So this is a very simple example of 1D Poisson equation. As a demonstration, this framework indeed works. And in this 1D problem, then because it's simple 1D, my G tilde is defined in a small interval with only 3 nodes, 2 boundary nodes, 1 inside node. And this is my data set for training, a single data point. This is my F, this is my U. One thing you may notice is my F is highly oscillated. The reason is when I try to train G tilde here from all the data sets, I would require my data set is sort of diverse. That's why when we generate this data set for this Poisson equation, we add oscillation into my F to make sure my data set for G tilde is diverse enough for training. So which means essentially we have some way to control how do we generate data set. For example, if my data set is a Q0 for F, then my solution is Q0. Then there's no way we can learn. There's no information there. Well, then after training, we can apply this framework for testing on new F. For example, on different shapes. But this probably is another limitation of this method. You can see here, all my testing case is sort of similar as my training, not significantly different, right? That sort of has similar shape, but the values can be very different. Still, you only train a single data point. It is impossible to generalize to arbitrary input. But it works well for the input I showed here. You can see this is a comparison of network prediction and the ground truth. This framework can be applied to diverse applications in different settings. For example, this is a 2D problem. It's a nonlinear problem. You can see the nonlinear square here, nonlinear Poisson equation, and also the geometry is complex. It's not square. It's a square with a hole. But still, after training, when you go to the new testing case, you can see the prediction compared to the ground truth. The accuracy is pretty good. We can even go to a PD system instead of single PD. So this is a diffusion reaction system in pulse media. So we try to predict the solution of the CA concentration CA and CB for different source FX. Still, if you look at the comparison here for the ground truth on the top row and the prediction on the bottom, they are very close. But we haven't really applied this scenario or this method to real application yet. There are still demonstration on some benchmark problems. Okay, all these methods have been developed based on our open source software called DeepSD. You can install DeepSD using pip. People install DeepSD or using Conda. Conda install DeepSD. So it has been used by many researchers in universities, nature labs, and also industry. Now we have, in addition to me and my group, we have other people around the world keep contributing new features into the software. So if you are interested, yeah, feel free to use it. It's also in open source in GitHub or adding new features. So the software is well structured and you need to modify the different components and develop new functionality. So with this, thank you for your attention. I'm happy to take any questions.
Questions? Thanks, Professor Lu, for the talk. There are two small questions I had. The first one was, a lot of your work is linked to Fourier operators, and those have been shown to scale at a very large data set and with lots of initial conditions. So in the case that we don't have like any initial conditions and we still want to generate some sort of ensemble predictions, do you have any ideas how can we go about that? And the second query was about in the case of data generation, when we have only a single input sample to learn the F mapping to J theta. In this case, can we think of this as simply as a data augmentation problem where we are masking some of the pixels and only taking some subsection of pixels with those initial conditions basically deciding what kind of function operator on that PDE space will work. So basically taking the same image, augmenting it every single time with a randomly generated mask of, let's say, binary, and then using that, whatever generated samples are there each time, thinking that we can learn like a function space from the mask from that. Yeah, thank you. Those two questions.
Okay. Yeah, for the first question, so in this operator learning setting, when we try to predict PDE solution, for example, from the initial condition, from the boundary condition. So I think your question is, if we do not have the initial condition, how to predict the solution? So mathematically, this is not possible, right? So if you do not have initial condition, there's no way to predict PDE solution. But if you have to do this, or if you assume my initial condition is not exactly known, but if we have some kind of information, then we could do something for it using the uncertainty quantification. Although we have no complete the initial condition, then by using uncertainty quantification, which means we do not predict a single prediction of the solution. Instead, we predict a distribution of my PDE solution. Then this can be applied. And there are actually many researchers and many works by extending the DeepONet or other methods from the standard PDE prediction from a single solution to a distribution using the UQ, the uncertainty quantification approach. Then for the second question, so here, if we do the training using the mask, for example, if we apply a CNN with input of F and output of U, we could do the mask for training for the mask given F, then try to generate the U. We didn't try this, but so I'm not sure how well it would work, but my intuitions may not work well. Because still, if you have, for example, if you consider, there are many works on the mask training or mask CNN, but they still require a data set instead of a single data point. Yeah, but then it's a good idea to try.
And thank you for the very interesting talk. I have one, the first question is quite simple. So for inference case of your operator learning, do you take both X and UX as input?
Let me go back to this. Yes. So here, let's say we should try to do a prediction. The short answer is yes. You need to predict the GU. We only predict a single prediction and a specific Y at one forward pass. But this can be parallelized, which means if you try to predict the solution of Y at that's a grid point, could be a dense grid, for a lot of different function U. What we can do technically, instead of point by point, as you can see, there's some specific structure of the network. So what we can do is we put the set of all the Y as included here. Then we do the forward pass using DeepONet. Then we get this output from DeepONet. Then we fix this. Basically, we store this information. Then for a new input function U, there's no need to recompute the DeepONet part. So this can be pre-computed or pre-processed in the prediction stage.
No, I mean for inference, I mean like for testing, you also have both as input.
Yes, we have both, but this part can be pre-computed to reduce cost. But mathematically, yes, we need both.
Okay, and the second question is more general. So the original motivation of doing this is to have a model which can predict an operator, and but in the end, what you have is again some model that works on either the initial input or the transformed input, and it is still specific to your specific case. Like if you change some parameters, you have to retrain your model, right? You again have like some operator level model in the end.
Okay, so yeah, of course, this is a black box neural network instead of a symbolic equation. So also this is your surrogate model. But it's easy to extend this. For example, people called MIONet for multiple input operator learning, which means instead of using a single input, let's say initial condition, boundary condition, or force or some coefficients, we can put all these together into my network training. So my network will have multiple branches. One branch for initial condition, one branch for boundary condition, one branch for coefficients, maybe another branch for a different coefficient. All this can be combined together for training. Then during the prediction stage, you can predict this PD solution then for arbitrary conditions.
Okay, very good. Thank you.
One last question from the round. Thank you for the talk. So if I understand, the input U is discretized at endpoint. And
yes.
This endpoint are given as Y. And we are learning the spatial basis as a function of the MX, of the MX points. Have you tried to, for example, compare this to in the case where this trunknet is a Lagrange polynomial, for example, of P1 finite element? Have you seen how it's compared? And the second question is, in the local mapping that you just presented, do you have any specific way to choose the next point on which you do the inference? So you learn on one shot, one point, and then you go to a second point. Is there any this flow of going from the first point to the second point? Is there any way to, or is it just a random point to jump from one point to the second?
Okay, yeah, for the first question, so here, what we have is a specific basis function learned by the network. But if you compare with classical basis, people apply in neural methods, as here we learn different bases for specifically as for different problems, then this basis would have better performance than classical basis. Actually, one interesting diversion is what people have done is you train a network, a DeepONet, for a specific function that's both equation. Then you extract the basis learned from the network. Then, of course, you do some post-processing, for example, normalization and so on. Then you compare with other bases for inspection method for solving new equations. So actually, this learned basis can have better performance than people manually design basis. Then for second equation, for the training of the gene delta here, so what we do is just either on the left, we draw a grid, or on the right, we do random. We haven't developed a specific way to select point, but I agree with you, there might be some smart way to select what the best point, but here we do just random or uniform.
Great. Thanks very much. Thanks for all the questions.